Welcome to my YouTube channel, and today let's talk about dynamic programming. I'm sure you guys have encountered this. In Leetcode, it's just basically you split the problem into smaller subproblems and you store the results. And then when you're solving on the given problem, you combine all those results from the smaller problems, and that's how you solve this problem. Typically in dynamic programming, you have two properties. The problem must have optimal substructure and overlapping subproblems. And there are two ways of doing dynamic programming. It's either memoization, it's a recursive top-down, and tabulation, that's bottom-up. For this, we will be solving 4 problems in total. So 2 problems that will be from Knapsack problems, and then 2 problems from Leetcode problems. And the most general problems that you see in dynamic programming. I skipped Fibonacci sequence problem because that's very easy, and I think you guys should have seen that problem before, so I just skipped that part. So let's look at the knapsack problems. So there are 3 types of knapsack problem. You have 0 or 1 knapsack, unbounded knapsack, and bounded knapsack. So for this video, I will be only talking about the first 2. Maybe next video I will talk about the third one. So basically in dynamic programming, you have to find the subproblems. What are the subproblems? You are shrinking the original problem, the size of the problem, either by looking at smaller knapsack capacity, or you are looking at the fewer items, and then you are building up your solution. So in this case, for 0 or 1 knapsack problem, we have to use both 1 and 2. Therefore, we have 2-dimensional DP matrix. For unbounded knapsack, we use only the first part. We are not looking at the second part. Therefore, we only have 1-dimensional dynamic programming array. So basically, just to keep in mind, knapsack problem, you have like on the right side, right bottom corner, you see 5 items. You are given weights and values. So given a constraint, say your knapsack bag has 15 weights, that's maximum, then you basically have to maximize the value, while items that go into your knapsack the total weight must be less than 15. So it's like an optimization problem, and it is an optimization problem. Two things going on. One is the pseudocode for 0 or 1 knapsack, and another one is the actual Python code for this problem. So at line 1, you are initializing dynamic programming DP matrix. That's dimension of capacity 1 plus 1 times length of weight plus 1. And here DP of I, j is defined as the maximum value that you can have in a bag of capacity I, with only considering the first j items. So let's see. So here, let's look at this. How do you update dp of I, j? Well, so there are 2 cases for dp of I, j. We can pick the j item, then the remaining item that we choose to put in the knapsack must be the optimal solution for, what do you think that is? That will be this guy, dp of I minus weights of j, so j's weight, comma j minus 1. And then you have to add these values of j, because we are picking the jth item. Or jth item is not used, then then there will be this guy. So and then we take the maximum. You take the maximum, and that will be optimal solution for dp of I, j. So remember there are 2 cases that you have to consider. Either you pick the jth item, or you don't pick the jth item. And the only time you can pick jth item is if this constraint is satisfied. Otherwise, there is nothing. Otherwise, you don't have to take the maximum. dp of I, j will be just dp of I, j minus 1. And that's it, pretty much. Explanation for the previous slide might not be sufficient, so let's look at specific example. So here we have a knapsack problem, and I just came up with 5 items. You can see on the right corner, and here on the top left, that's the two-dimensional matrix that we have to fill out. So the rows are what? That's the capacity. So here our knapsack capacity is 12. So that's why you only have, so the last row, that's 12. So you had 13 rows. And then we have 5 items. So here you have 6 columns. We initialize the first row and then the first column, P of 1, 1. Now since weight, so zeroth weight is not less than or equal to 1, so dp of 1, 1 will be just dp of 1, 0. So we just, so this guy's value will be this guy's value. Here let's look at dp of 5, 1. So we initially set dp of 5, 1 by the value at dp of 5, 0. So there will be just 0. Now since the zeroth weight, which is equal to 5, that's less than or equal to 5 here, so we have to take the maximum. So we can either choose this first item or not. So that's why you are taking the maximum of dp of 5, 1, or you take the value, the first items, and that value will be this values of 0, and then you have to subtract this from the 5, and then that will get you 20. So dp of 6, 1. So we initially set dp of 6, 1 by the value of dp of 6, 0. And then you see that weight, the zeroth weight, the first weight is 5. That's less than that is definitely less than 6. So you have to take the maximum of either you choose that item or you don't. So that's how you get this guy. So dp of 6, 1 is 20. Here I fill out the second column, second item, and the second item's weight is less than or equal to 3. So you take the maximum of dp of 3, 1, this guy. That will be if you are not picking the second item, or here the second part is if you pick the second item, and then you take the maximum and you get 13. The cell below, basically the same idea. We take the maximum of not picking the second item, or you pick the second item. Again, same idea. You take the maximum of whether you pick the second item or not, and then you get 33 by filling out this table, and you return that value. So dp of 12, 5. So 12, 5, that's 48. So that's the answer for today's video. So here we have an unbounded knapsack. That means you have unlimited number of unlimited items. There are no constraints. The only constraint is the capacity. And here, if you look at the code, it's actually a lot simpler. So dp of x would be the maximum value that I can have in a bag of capacity x. So for this problem, it's actually better to look at the simple example and see how this code really works. This example, here we only have 3 items for the sake of simplicity, and let's say our knapsack's capacity is 4. So here I created a 2-dimensional matrix, but if you look at my code, it's actually just an array. So this each array, it corresponds to the knapsack's value. So here initial, that means the knapsack's capacity is 0. Here the capacity of knapsack is 1, capacity of knapsack is 2, 3, and 4. So our answer will be here, and let's look at how this runs. So when knapsack's capacity is 0, then everything is just 0. So there is no questions about that. When our knapsack's capacity is 1, then we iterate this, and here we see that, so the first item's weights, that's 1, that is less than or equal to this guy. So we take that one. So we choose items A, and then we take the maximum. So here, so dp of 1 would be, what do you think that is? That's 0. And then here dp of 1 minus the first weight, that will be 1. So 1 minus 1, that will give us 0, right? And then you have to add values. The first value, that will be 2, and you take the maximum. So that's how you get 2. Looking at the second iteration, and if you can see the third entry here in this row, here I is equal to 2, that guy. And so we can choose the second item, which is what? So second item was this guy. Let's pick that one. So we have a dp of 1 plus values of 0. That will be what? That's just 2 plus 2. And then we have a dp of 2 minus 2 plus values of 0. So that's dp of 0 is this guy, plus values of 1, that was 3. So and then we take the maximum, so that's 4. And you do that again for the last array, and then that's how you get the answer. If my explanation was not enough, then I really encourage you to run this table. Then I think you will have perfect understanding. So just I really encourage you to come up with like simple example, 3-4 items maximum, and then run it. Yeah. Our first Leetcode problem on dynamic programming. So this title is coin change, and let's look at this problem. So we have an unlimited number of each kind of coin, and that should ring a bell that this might be similar to unbounded knapsack problem. However, so the concept might be the same, but then the algorithm itself is not exactly identical. So let's look at this. So we have amount 5, and we are given coins 1, 2, and 5. And how many ways can we make up the amount 5? There are 4. 5, 2, 2, 1, 2, 1, 1, 1, and 1, 1, 1, 1, 1. And notice that here, so we have a combination. So order doesn't matter. And the same thing here. And one thing that you have to keep in mind. Let's say amount is 0, and you are given some coin. I don't know, let's say 2. Then what do you think that output should be? Output should be 1, right? I know it sounds strange, but how many ways can you get an amount 0? Well, you don't pick anything, so that's just empty. Yeah, I know. It's a little that small technicality, but yeah, that's one edge case that you have to consider. Coins 2, 3, and 5, and amount 10. So I come up with that example because the example we just saw is a bit too simple, and there are four combinations to get to 10. So that's my hint 1. So from the problem, we have infinite number of each type of coin. We already had unbounded knapsack problem. So while the code for this problem is not identical to the code we saw for unbounded knapsack problem, the idea is very similar. So here, how do you find? So the key is to find the subproblem and then somehow find the recurrence relationship. Let's say let's say we have a dp of k, j. What does that mean? So that means we have a number of combination that can make up amount j, and we are only using the first k coins. Now, suppose we want to move to the next part. So that means we are looking at dp of k plus 1, j. This means we are looking at the first k plus 1 coins. Here we only look at the first k coins, but the next part will be we are looking at the k plus 1 coins. So we are looking at one additional coins that comes after k's coin. Now, what should this guy be? I mean, I already gave you the answer, but here, if the kth coin is less than or equal to j, so j will be the amount j here, then it's very similar to the one that we just saw. So you have to consider that portion too. So dp of k plus 1, j would be, what is it? That's number of combinations that make up an amount j, but only using the first k coins plus. So that part is just dp of k, j. So we are only using the first k coins, and then if the kth coin is less than or equal to j, then we have to consider we can pick that coins. So there will be number of combinations that make up amount j minus coins k plus 1, and then using the first k plus 1 coins. I think I have a typo here. I think this one should be coins of k plus 1. I'm so sorry about that. So you have to add those two numbers, and yeah, and that's it. And so here the condition is that if coins of k plus 1 is less than or equal to j. Otherwise, you have dp of I minus 1 comma j. So sorry about like changing from k to I. And yep, so let's create two-dimensional dp matrix. And then the first row corresponds to 0 coins selected. So dp of 0, 0 is 1 is an example. And if you look at here, so the first row corresponds to 0 coins, and only this guy is just 1, and all other entries are equal to 0. And the second row corresponds to picking only the first coin. Here the third row corresponds to picking only the first 2 coins, and here the last row corresponds to the picking the first 3 coins, and then we just iterate. So here let's look at this. So this guy, so there will be coins of, so dp of 1 comma 0, and since coins of 0 is bigger than this guy 0, so we set this equal to the entry above. So just so bring this guy into to here, and so same thing here. And here let's look at this. So the first coin is less than or equal to 2. We add 2 numbers, so dp of 0, 2 plus dp of 1, 2 minus coins of 0. Okay, so and then you add them up and you get 1. So dp of 0, 2 is this guy, and dp of 1, 0 is this guy. Because remember coins, the first coin's weight, the first coin was, I think it was 2. It was 2. So when you choose that, you have to shift this by that amount, and you are looking at this guy. Same thing here. Coins of 0, so the first coin is 2. That's definitely less than or equal to 3. So you do the same thing again. You are looking at this number, and then you add dp of 1, 1. So that's this guy. Since both of them are equal to 0, and you add 0, you add 0 plus 0, you get 0, and you do the same thing again. And then the next row, we are looking at the first 2 rows. First 2 coins. Basically you do the same thing, and let's look at this one. So the second coin, I think there was 3, and that's definitely less than or equal to 6. So we have dp of 2, 6 will be the one above here, dp of 1, 6. So that corresponds to you are not picking the second coin. And if you pick the second coin, and that will be, you are looking at this guy. So 2, 3. And then you add them up, you get 2, and you do that again. Now here is the last row, and you basically do the same thing, and you return this guy. My Python code for that problem. And if you notice, I actually have 2 versions. So the first one is that I'm using 2-dimensional dp or matrix, and then the one below is just an array. If you notice, if you look at this guy, you don't need to have 2-dimensional dp matrix. So when you're working on this guy, you only need to know the row above. When you're working on the last row, you only need to know the row above. You don't need to know like the first row or the second row. You only need to know the third row. Then you can complete the fourth row. So that's the key idea behind this. And the code, and let's run this. And so it wasn't too bad, right? It was very similar to the unbounded knapsack problem or second Leetcode problem. I know it is labeled hard, but I don't think this is really that difficult. I would say this is definitely medium problem, or actually it's not really that hard. It's actually one of the few hard problems on dynamic programming that I got it right on my first try. And so my advice is that even if the problem is labeled hard, like, don't get scared. So let's look at this problem and let's see how we can do this. So this is how I approach this problem. I know it seems like a lot is going on, but actually it's not. So let's look at this. So this guy is just how I use graph to represent all the rules. So if a letter starts with A, then the next one must be E. If a letter starts with E, I mean if we are given character E, the next one must be either A or I, and so on. So this is the rule. And so how is this really related to DP? So let's find the subproblems. So let's say DP of J is the total number of strings formed by these rules, and how is this number depends on the previous state, DP of J minus 1. When you find a relationship, this problem is pretty much done. So let's use that example. So here, let's say we have, I don't know, we want to find, what was it? Here we have n, so we are given n. So here, let's say n is equal to 2. Now, so there are 10 possibilities. So how do we go from here, these 5 choices, to 10 choices? So one method that I encourage everyone is that try to think how to change this graph so that it's actually it is helpful for us to solve the problem. So instead of looking at this, so how about we start with this? So we are looking at the previous state, and if the previous letter ends with E, then the next one must be A. If the last character of that string ends with I, then the next one must be A. Same thing, if the last character of that string ends with U, then the next one must be A. So here I'm not changing anything. So here, think of this as moving this guy into here. Now, why do I do this? So that's a very good question. So same thing for A. So A to E and I to E, and so on. Yeah, let's see. So let's say for DP of 1. So for DP of 1 we have A. So A subscript ord, E subscript ord, I subscript ord, O subscript ord, and no, actually so for DP of 1 we have A underscore ord, E underscore ord, I underscore ord, O underscore ord, U underscore ord, and they are all equal to 1, and we add them up, and that's how you get 5. Now for the DP of 2, this is what we are interested in. It would be actually, you are summing up basically A underscore new, E underscore new, I underscore new, O underscore new, and U underscore new. Let's look at A of new, A underscore new. That's just E underscore ord plus I underscore ord plus U underscore ord. That's equal to 3. Now, what does that mean? Well, it means that A underscore new is equal to 3, and that is true because if you look at here, how many strings end with alphabet A? That's EA here, we have IA here, and then UA. As you can see, EA, so after E we have to add A, and here after I we have to add A, and after U we have to add A. So this is the recurrence relationship. This is my Python code for this problem, and as you can see, you initially set A underscore ord, you set all of this guy equal to 1, and then you initialize them by adding them up, and then you are iterating from the number 2 all the way to n. So and then you update a underscore new, e underscore new, I underscore new, o underscore new, and u underscore new, and then you add them up, and then you do the modular operation, because number can get very large, and then you set them, and then you set a underscore old by a underscore new, and you do the same thing for the remaining 4 numbers, and then you return the last number. That's it. I know this is like very short code, but so let's see how this works. Code that you just saw, and let's run this. Yeah, so this is it, and I hope this, and so for the next video on dynamic programming, my goal is to have about 15 problems from the Leetcode or hacker ranks, or maybe some real problems that I that I learned from my dynamic programming course. It's not really, I would say, like these kind of interview problems, but it's really helpful. Like if you are in machine learning, then let's say hidden Markov model like HMM. The idea behind so I think the idea behind that is using dynamic programming. So, and not only that, like reinforcement learning, and so you are using a lot of dynamic programming, not just in machine learning, not just for this kind of like Leetcode interview problems, but then also operation research, optimization problem, which is really a huge field, and even in partial differential equation. So yeah, I think so for the next video, I'm hoping to get 15 problems, 5 minutes for each problem, so that would be 75 minutes, still 1 hour and 15 minutes. But yeah, I just want to make my video short, so that I'm not wasting any of your time. And yeah, I hope you guys all had a great weekend, and I'll see you next time. And if my video helps, um, I really ask you to subscribe my channel, so that you guys can get timely notification, and it really helps growing my YouTube channel. Thank you so much, and I'll see you next time. Bye bye.